So when we talk about 3000 cubic meter blast furnace, we are not just discussing a scale. We are discussing the kinetic energy balance required to sustain a massive industrial reaction. So look at the central diagram on your screen, the blueprint of our Titan. You will notice complex thermal formula on the left and right, like the gas temperature calculation, which is the stove temperature minus thermal loss. So today I am going to walk you through three critical deliverables. So first, how to engineer a furnace to reliably hit a 5 million ton annual target. Second, the dumpy profile philosophy that exceed campaign life. And third, the volumetric synthesis required to validate a 300 cubic meter design. So let us have a focus on the blue and orange nodes on the furnace profile. These represent the critical monitoring point where the thermal and mechanical stresses are highest. So understanding these interconnected variables is the difference between a high efficiency run and a catastrophic operational failure. To understand the architecture, we must first define the massive production throughput this physical structure is engineered to sustain. So look at the bold figure on the left. So that is our North Star. To achieve this is a modern plant using two furnaces as shown in the middle right icon. Each unit must be workhorse. If you follow the data to the top right, you will see our required daily output is exactly 7,333 tons. This calculation is based on 355-day working years, accounting for necessary maintenance windows as indicated by the calendar icon at the bottom right. The so what factor here is simple. If your physical architecture cannot reliably sustain this continuous throughput, your face is cascading failure across the entire steelmaking chain. The notes at the bottom emphasize that every weld and refractory brick must be engineered for this massive continuous mass flow. This daily target is the fundamental driver for the volumetric requirement we are about to calculate. Now that we have our daily production target of 7,333 ton, we need to determine the exact effective volume required to house that reaction. So coming to our this slide, which is focused on the effective volume deduction methodology. The flow sheet represents the mathematical heart of our design. We take our daily output of 7,333 ton, factor in a coke ratio of 0.45 and multiplied by a smelting ratio of 1.1 to arrive at our target, that is 3000 meter cube. Note the icon in the center, the factory icon for output, the coke pile for the fuel and the flame for the smelting intensity. We have optimized the coke ratio specifically for fuel efficiency and CO2 reduction. Meanwhile, the smelting strength is dictated by our intensive reduction requirement. The core insight here is that the effective volume is the anchor constraint. Every physical dimension we discuss from here on the hearth diameter, the waist, the throat is a mathematical derivation of this 3000 cubic meter requirement. If your volume is off, your kinetics will never stabilize or meet the annual demand. So with our 3000 cubic meter volume established, we must decide on the furnace's physical shape, specifically why we favor a wider dumpy profile. So coming to our design philosophy, observe the comparison on screen. On the left is a I've got a legacy profile, tall and narrow. In the center, highlighted in glowing blue, is our modern 3000 meter cube profile. If you look at the table on the right, you will see the modern profile is shorter and wider. Why? Because unilateral scaling fails in metallurgy. A wider hearth and waist allow for higher capacity and a lowered coke ratio, which significantly boosts efficiency. So, most importantly, this dumpy shape provides an extended service life. By decreasing the height to width ratio, we balance smelting strength with the longevity while improving the overall operational condition within the burden. This geometric philosophy ensures that the furnace doesn't just run hot, it runs long. We are not just building a reactor, we are building an asset that must last 15 to 20 years without failure. Now, this wide efficient profile is then segmented into five distinct zones, each serving a specific role in iron making process. And based on our this slide, which is all talking about the preceding statement. So the diagram here shows the vertical segmentation of our Titan standing at total effective height of 29 meters. Follow the level on the right side of the furnace from the throat at the top down through the body, a shaft, waist, the abdomen or the boss, and finally the hearth at the base. Each of these zones is precisely sized to facilitate uh, the physical transformation of iron ore from a solid burden into molten pig iron. The so what here is the thermal gradient. If the height is not segmented correctly, you risk incomplete reduction or hanging of the burden. The 29.2-meter height is the result of balancing the residence time of the raw material with the upward velocity of the blast furnace gas. It is a vertical race between descending solid and ascending gases. Achieving this height correctly ensure stable gas distribution and maximum productivity. So let's look closer at the top of this vertical race, starting with the throat and the furnace body. So throat and body, if you see, zone 1 is the throat with a height of 2.5 meter and a diameter of 8.8 meter, creating a volume of around 152 meter cube. Its primary job is controlling material running and upward airflow distribution. So below that is zone 2, the furnace body or the shaft, which is the largest segment at 16-meter height. Note the angle 82-degree indicated by arrow. This specific angle is sized to accommodate optimal furnace particle flow and maintain coke strength as raw material descend and begin reduction. The so what factor for the shaft is permeability. If this angle is too steep or too shallow, you will see uneven gas distribution which leads to increased fuel consumption and poor hot metal quality. We are the engineering the descent of the thousands of tons of material every hour. As the burden descends through the shaft and reaches the point of complete reduction, it enters the widest part of the furnace, the waste. So look at the glowing orange core in the center of the diagram. Zone 3 is the waste or maximum diameter at 13 meter, providing a volume of around 265 meter cube. This dimension is critical because it directly dictates the permeability of the slag. If it is positioned precisely where uh, unrestored ore is completely reduced, moving down your 4 is the abdomen or boss, standing 3.5 meter height with an angle of 79.5 degrees. Notice how the arrows show the profile narrowing towards the bottom. This shrinking geometric angle matches the rapid reduction in material volume as solid ore melt into liquid iron and slag. If the Bosch angle doesn't match this melting rate, you get erratic pressure swing. So we are essentially designing a funnel that accounts for the state change of the matter passing through it to ensure a smooth flow. The molten material eventually settle at the base of the furnace in the hearth where we have implemented a vital protection feature. So now we reach the crucible zone 5, the hearth, which has a height around 5 meter and a dia of 11.7 meter. This zone determines your absolute burning amount of coke and primary iron output capacity. It acts as a crucible storing primary iron and slag. But look closely at the dashed blue line at the bottom. The dead iron layer will maintain a permanent liquid buffer with a depth of 2 meter. The so what factor here is a campaign life. This dead iron layer protects the refractory lining from the extreme thermal and mechanical erosion at the very base. Without this 2 meter buffer, the turbulent molten iron would eat through your hearth floor in a fraction of intended service life. So we are using the product itself to protect the machine that makes it. So to maintain the heat and the chemistry within the hearth, we need a sophisticated air distribution system, which led us to the tier architecture. And as you can see, this top down view shows the engine room of the furnace. To maintain uniform combustion and a blast distribution across an 11.7 meter diameter crucible, we require exactly 28 tier vents. So this is not a guess. It's a calculation based on the formula shown on the left. N is equal to that 3.14 multiplied by D divided by 1.3. The blue arrows radiating from the center illustrate the blast distribution. The so what here is radial uniformity and the raceway adiabatic flame temperature our raft. If you have too few vents, you get dead zones in the hearth where the temperature drops leading to slag buildup and drainage issue. So by using 28 vents based on the strict central distance calculation, we ensure the raft is consistent around the entire circumference. This is how you ensure high melting intensity without a localized refractory wear or a operational instability. So with all these zones and component defined, we must now synthesize the data to ensure our total volume meets the 3000 cubic meter requirement. So now let us see the table on the left. This is our final mathematical check. We have listed every stage from the throat down to the hearth with their respective heights, diameters, and calculated volumes. So when you sum up the volume of all 5 zones from 151 to 656, you get a total 2922. So the stacked blocks on the right visually represent this synthesis, showing how each zone contribute to the whole. So these validate the 3000 meter cube design threshold. The so what factor is simple. This is the proof that our physical architecture matches our theoretical production goal. We have successfully translated a 7333 ton daily production requirement into verified physical volume of roughly 3000 cubic meter. So every piece of the puzzle fits perfectly to support the massive load. This brings us to our final conclusion, the master blueprint that integrate every calculation we have discussed today. And here is the result of our engineering, the master blueprint about which we are talking. So every dimension you see from the 8.8-meter throat to 11.7 hearth is mathematically interlocked. The synthesis statement on the left is the key takeaway. Every dimension is tied to the internal kinetics. These carefully proportioned five-stage architecture successfully transform the raw demand of uh, almost 5 million tons per year into a highly efficient, high capacity, and long life industrial reality. We have balanced the total height of 29 meters with the dumpy width of ensure operational stability for years to come. As engineers, our job is to ensure these numbers hold up under the extreme heat and pressure of furnace floor.